In this video, we'll commence our look at motion. We'll start off by looking at distance and displacement. We will also look at their graphs. We'll look at displacement time graphs, distance time graphs, and we will analyze each graph to see how the body's speed and velocity and acceleration are changing. So let's look at distance. What is distance? Now, as previously defined, distance is defined as the path length between 2 points. So distance is defined as the path length between 2 points. Right? So for instance, if a body starts at A and travels along a path like that to B, then the distance traveled is the length of the actual path taken. Right? So the distance traveled will be the length of the actual path taken. Now, the SI unit of distance is the meter, m. Right? Of course, you know that there are other units like the kilometer and so on, but the SI unit is, of course, the meter. Now, distance, of course, is a scalar quantity, which basically means that it has magnitude only, right? So, distance is a scalar quantity, meaning that it has magnitude or size only. So, we talk about distance. What we should also mention is that the symbol for distance is a lowercase s. Now, in some books, you may see the letter x, so we'll add that as well. So, the symbol for distance is an s or an x, depending on the text you may use, right? So, since we look at distance, we'll now basically look at distance time graphs, right? We will look at distance time graphs. Now, what is a distance time graph? A distance time graph basically is a graph which shows how a body's distance or the distance traveled by a body varies with time. All right? So we'll look at distance time graphs. So these are graphs which show how the distance a body travels varies with time, right? So typically, distance on the y-axis and usually in meters, right? Usually in meters is plotted against time, which of course goes on the x-axis and is typically given in seconds, right? So usually a displacement time graph will basically have distance on the y-axis in meters and time on the x-axis in seconds. But of course, there may be other units used as well. You may see distance in kilometers, you may see distance in hours, time in hours and so on, but typically we use the SI unit, and of course the SI unit of distance is the meter and the SI unit of time is the second, right? So what we'll do next is we'll look at basically different distance time graphs for particular states of motion, right? So let's look at a few distance time graphs. So we have a distance s in meters and time t in seconds on the horizontal axis, right? The first graph we look at is a simple horizontal line. We'll talk about that one later. So let's call that graph 1, a horizontal line, all right? The second one starts at the origin and slopes upwards. We'll call that graph 2. The third one starts at the origin and also slopes upward, but of course this time it's a steeper slope and we'll call that graph 3, right? Now the fourth graph we will examine is not a straight line but is a curve. So we'll draw this one like this. Right? So let's call this point O. Now up to this point it is curving, and here let's call this A, and this point B is a straight line, right? And C, it basically curves, well, it starts to curve again, and at C it becomes flat, right? So these are some examples of distance time graphs, and we'll basically examine each and we'll use them to determine the state of motion of the particular body, right? So say that distance time graphs, of course, involve distance on the y-axis being plotted against time on the horizontal axis, right? And there are certain pieces of information we can obtain from a distance time graph, and one such information is the speed, right? So how do we obtain speed from a distance time graph? So from a distance time graph, we say that the gradient of the graph gives the body's speed, right? So if we have a distance time graph and we want to determine, say, the speed of the particular body for which the graph is representing, then we basically have to look at its gradient, right? So what we'll do is we'll analyze each of these graphs, and we'll then basically determine what is happening to its gradient and hence what is happening to its speed. Now let's look at the first graph, graph 1. Graph 1 is a horizontal line, and because it is a horizontal line, the gradient is 0. So graph 1 is a horizontal line, and so the gradient is 0. Now, since the gradient of a distance time graph represents speed, then this would imply that the body's speed is equal to 0. And if the body's speed is equal to 0, then this further implies that the body is stationary, right? So the speed is equal to 0, then this means the body is stationary. So the body is simply not moving. So if we want to look at a stationary body, or the distance time graph of a stationary body, it is simply a horizontal line, right? So if you notice, the distance is at some value and it is not changing, and it is therefore constant. And because the distance is not changing, that can only mean one thing: the body is simply not moving. So the body is not moving, its speed is 0, hence the body is said to be stationary, right? Now let's look at graph 2. Is graph 2 a horizontal line? No. It is a straight sloping line, and of course we describe the gradient of this line as being constant or uniform, right? So graph 2, the gradient is constant or uniform. And again, since gradient represents speed, then this means the body's speed is constant or uniform. So graph 2 basically shows a body which is traveling at constant speed, right? And by constant speed, we mean that basically the speed is not changing, right? So usually that's what the word constant means. Later on, when we look at speed, we'll define speed and we'll talk a little bit more about what it means exactly for a body's speed to be constant, right? So graph 2 basically shows the graph of a body which is actually traveling or moving with constant speed, right? Now let's look at graph 3. Now graph 3 is also sloping upwards, but this time it has a steeper slope than graph 2. So because it has a steeper slope, which is also uniform, it is also traveling at a constant or uniform speed, but this time it is traveling at a higher speed than in 2, right? So graph 2, graph 3, gradient is constant or uniform as well. So gradient is constant but steeper. So steeper than that in graph 2. So therefore this represents a higher constant speed. Right? So graph 3 shows a straight line with a uniform or constant slope, and this therefore means that the speed is uniform or constant. But of course, because graph 3 has a steeper slope than graph 2, its gradient is larger and therefore its speed is larger. So graph 3 represents a body which is moving at a constant speed but at a higher speed than that in part 2. Right? So we've examined 3 of the 4 graphs which we plan to look at. Now let's look at the 4th. Now the first 3 graphs represent straight lines. The first one is a horizontal line, 0 gradient, 0 speed, body stationary. The second is a straight sloping line with a uniform slope, so it therefore represents a body which is moving at a uniform or constant speed. The third represents a straight sloping line with a uniform gradient as well, but this time this line is steeper than that in 2, and therefore this body, while traveling at a constant speed, will be traveling at a higher speed than the body whose graph is represented by 2. Now let's examine the graph 4. Now graph 4 is not a straight line, but it's actually a curve. So what we will do is we'll analyze different sections of the curve by looking at its gradient, and will therefore tell what is happening to its speed. So if we want to analyze this one, graph at O, it is basically flat, horizontal. As it moves from O to A, it starts to curve upwards. Now between A and B is a straight line, and then beyond B, it starts to curve downwards, it starts to get flat. And at C, it eventually flattens, right? So we say that basically at O, the gradient is 0, right? This means, of course, the speed is equal to 0, which therefore means that the body is at rest, right? So at O, the graph is flat, right? The curve is flat. So therefore, the gradient is equal to 0, which means the speed is equal to 0, and therefore it means that the body is at rest, right? Now let's examine the region OA. Now OA, it starts to curve upwards, and therefore this means that the gradient is increasing, right? So the gradient is increasing. So the curve, the graph curve upwards. Right? The gradient increases uniformly. Now, you might not be able to tell that the gradient is actually increasing uniformly from this curve, but of course, just take it that the gradient is actually increasing uniformly. And if the gradient is increasing uniformly, then this means that the body's speed is increasing uniformly, right? And of course, if the body's speed is increasing uniformly, then this means that the region OA represents uniform acceleration, right? So we therefore say that the body accelerates uniformly. So basically, we're able to gather all that information by simply analyzing the gradient of the section OA. Right? Now, in the graph, it might not look it, but as I said, OA is curving upwards, and AB is a straight line, and beyond B, it starts to curve downwards, and again, at C, it has once again become flat. So let's examine AB. Now, AB, as I mentioned before, is a straight line segment of uniform slope, right? So we say that this is a straight line segment of uniform slope. So we say that the gradient is uniform, which of course implies that the speed is uniform. Right? Now BC, from B to C, the graph starts a curve. It's becoming less steep, right? So it is becoming less steep. So the graph curves downwards. The graph is curving downwards, right? So the graph is curving downwards. Right? This means that the gradient of the graph is decreasing. And of course, once again, we know that the gradient of a distance time graph represents speed. And if the gradient is decreasing, then this means that the speed is decreasing. Right? And because the speed is decreasing with respect to time, we say that the body is decelerating, right? So therefore the body is decelerating. So the body, it is decelerating, it is slowing down, right? And at C, the graph once again is flat, and this therefore means the gradient is 0, which of course means that the speed is 0, which further implies that the body is at rest. Right? So this basically analyzes the motion of the body whose graph is represented by the curve OABC. Right? So once again, we used the body's distance time graph to analyze its motion by examining the gradient of the graph. In sections where the gradient was 0, or the graph was flat, then the speed was equal to 0 and the body was at rest. If the gradient, of course, is uniform, then it means that the body's speed is uniform, right? We also showed what it meant, or two sections rather, with uniform speed, but of course one was steeper than the other, it had a larger gradient and therefore a higher constant speed. And then of course we showed the graph of a body that was basically accelerating. Now, accelerating in this case means a change in speed, right? And so the body was initially at rest, the graph was initially flat, which means the gradient is equal to 0. Then it starts to curve upwards, meaning that the gradient of course is increasing from 0. The gradient is increasing, and therefore the speed is increasing. Between A and B, it is a straight line, right? And therefore the speed is constant. So essentially, from O to A, the body accelerates to a particular speed, and then between A and B, it basically maintains that speed. So between A and B, the speed is constant, and then between B and C, the body starts to decelerate, the speed is decreasing, and eventually at C, the curve becomes flat, and once again, the body is at rest.